Here's a question. You have a list of numbers and a target. Pick 3 of them. Whose sum lands closest to the target? Not equal to, just closest. We might land above, we might land below. We want the sum that misses by the smallest amount. Let's use this example. Numbers are -1, 2, 1, -4. Target is 1. Try the triple -1, 2, 1. That sums to 2. We missed the target by 1. Pretty close. So we return 2. The sum, not the indices. Different from 3 is sum, where we return the triples themselves. Okay, try the obvious thing. Pick every 3 numbers, add them, keep the one closest to the target. With 4 numbers, that's 4 triples. Easy. Pause for a second though. What if the list had 500 numbers? 3 nested loops. The work grows like the input cubed. For n equals 500, that's tens of millions of triples. It'll run, but it's wasteful. We should be able to do better. Let's see what we're throwing away. Remember 3 sum. We sorted the array, fixed one number, and used 2 pointers for the other 2. Same shape here. We still pick 3 numbers. The only change is what we're chasing closest, not exactly equal. So sort first. Once sorted, small numbers sit on the left, big numbers on the right. That's the magic ingredient. Fix one number. Then put a pointer at the left of the rest and a pointer at the right. Here's the move. Add the 3. If the sum is too small, slide left in. If too big, slide right in. You might think we need to remember the best triple. We don't. We just need the best sum. Track one number, the closest sum so far. How do we measure closeness? The distance is how far the sum is from the target, ignoring the sign. The smaller that distance, the better. Let's walk it. Sorted array is -4, -1, 1, 2. Target is 1. Start with best sum equal to the first triple we see. Fix index 0. That's -4. L starts at index 1, R at index 3. Sum is negative plus -1 plus 2. That's -3. Distance from target 1 is 4. Worse than our best, which sits at distance 5. Update best to -3. Sum was -3, target is 1. We're too small, so slide L to the right to grow the sum. Now -4 plus 1 plus 2. That's -1. Distance is 2. Best drops to -1. Still below target. Slide L right again. But now L and R collide. Window closed. Move on. Fix index 1. That's -1. L is index 2, R is index 3. Sum is -1 plus 1 plus 2. That's 2. Distance 1. New best. Sum is bigger than target. Pull R left. L meets R. Inner loop ends. We've checked everything that matters. Notice what just happened. For each fixed number, the 2 pointers swept the rest in one pass. The sorted order told us which way to move every time. We touch each pair at most once per fixed index. The work grows like the input squared, and the sort is cheaper than that. Let's see the code. Sort the array, then seed best with the very first triple. Now we always have something to compare against. Outer loop fixes one number. Inside, left starts just after it and right starts at the end. Compute the sum. If it sits closer to the target than the best we've seen, update best. Move the pointer based on which side we missed. And if the sum equals the target exactly, distance is 0, we're done. And that's the pattern. Sort, fix 1, sweep 2, adapted from exact to closest by tracking distance. Same trio, different goal.